So this is going to be our second take on this. I'm having to re-record the audio here. So we're going to be talking about relative growth rates. And our key question is going to be, does a function f grow faster, slower, or at the same rate as a function g? Now, growing faster is not the same thing as being larger, and that's a fundamental point of confusion. So let's say I had two functions. Let's say that one of them was y equals x and one of them was y equals 2x. We would normally think that y equals 2x is almost always going to be on top as you go towards infinity. It's going to be over y equals x. But those are considered to grow at the same relative rate. The idea is that they are relative growth rates. So everything that's linear would have the same relative growth rate. So let's get a formal definition going on what I mean here. Sorry about the pause here. For x that is large, so it's important that we're talking about as we go towards infinity, so x has to be large, f grows faster than g, or we can say g grows slower, if the limit as x approaches infinity of f of x over g of x goes towards infinity. We could also say the limit as x goes to infinity of g of x over f of x is equal to 0. Now, they have the option of growing faster, slower, at the same rate. So what would the same rate look like? Well, we say that f grows at the same rate of g if the limit as x goes to infinity of f of x over g of x equals any constant that is not 0. So, one way we can think about this as a contest between the top function and the bottom function. If the top function is faster, it will go towards infinity. If the bottom function is faster, it'll go towards 0. And if they grow at the same rate, it's going to go towards any constant in between. So if you look at my graph here, if the top wins, we go to infinity. If the bottom wins, it approaches 0. Anything else in the middle is a tie. We say they grow at the same rate. All right, let's look at a couple examples of that. So for our first example here, let's say that f of x is x squared plus 2. And we'll call g of x e to the x. So we're going to establish, now it does not matter which one you put on top and which one you put on bottom to do this, as long as you remember how the rules work. So I'm going to choose to put my f of x on top here. And if we try to plug in infinity, we get infinity over infinity, so we're going to apply L'Hopital's rule. The top will become 2x, and the bottom will become e to the x, because the derivative of e to the x is e to the x. So we would have to apply L'Hopital's rule again, and we're going to get 2 over e to the x, which would be 0, because e to the x is infinity there, 2 over infinity is 0. This means that the bottom function won. So that means e to the x grows faster than x squared plus 2. Let's look at another example real quick. Let's compare two polynomials. Let's compare, let's go with a linear function and another linear function. Let's do the example we were talking about earlier here. So we don't need to apply L'Hopital's rule here. If we put f of x over g of x, the x's will cancel and we'll get 2 over 1, which would just be 2. Because the limit as x approaches infinity of a constant is just equal to that constant. And that is something between 0 and infinity, so they would grow at the same rate. Now sometimes we'll use a concept called transitivity. We've dealt with transitivity before when we talk about things that are less than or greater than or equal to. If A is equal to B and B is equal to C, then A is equal to C. But how does it apply in this circumstances? Well, if F is slower than G, which is slower than H, then we know that F is slower than H. And we could reverse those statements for faster. If F is faster than G, which is faster than H, then F would be faster than H. Now, we could also use it for growing at the same rate. If f of x grows at the same rate, that's what that symbol means, as g of x, which grows at the same rate as h of x, we can be guaranteed that f of x and h of x grow at the same rate. That should say h of x. F of x grows at the same rate as h of x, not g of x there. Now, the one thing we can't do is if we know that f is slower than g, and we know that g is faster than h, we're not going to be able to tell anything about f and h. We don't know which one's faster, which one's slower, if they grow at the same rate. We just won't know. So let's move on to some more examples here. So example 3, let's call f of x natural log of x and g of x let's do it cubic, x cubed minus 3x squared plus 2. So sometimes choosing which one goes on top can make things easier. Here I'm going to do ln x. If you have a natural log, a lot of times it's easier to put it on top. It's not necessary though. So if we plugged in infinity, we get infinity over infinity. So I'm going to apply L'Hopital's rule here. And when we do that, remember the derivative of ln x is 1 over x. And the derivative of the bottom is, of course, just 3x squared minus 6x. So I'm going to use some algebraic tricks here. This is not L'Hopital's rule. This is just me taking the 1 over x on top and distributing it onto the bottom. You can also think of it as dividing by something the same as multiplying by the reciprocal. I get 3x cubed minus 6x squared. Now, if you plug infinity in there, you get 1 over infinity, which is, of course, just 0. This means that the bottom function wins. So the bottom function has to be growing faster than the top function. So g of x is faster than f of x. All right, example 4. Let's let f of x be natural log of x and g of x be, let's do another logarithm, log base 2, or no, let's go 5, log base 5 of x. So limit as x goes to infinity, again, doesn't matter which one goes on top, ln x over log base 5x. A lot of people forget the rules for logarithm derivatives. So derivative of, we're doing L'Hopital's rule because we get infinity over infinity. Limit as x goes to infinity. Natural log of x derivative is 1 over x. But for log base 5, remember it's 1 over x times the logarithm of the base. And I'm going to apply an algebraic trick here that dividing by something is the same, or the 1 over x on top and bottom cancel, so you get 1 over ln 5. Now, that is a constant. 1 over ln 5 is a weird number, but it is just a number. This means that the two logarithms shown grow at the same rate. Anytime we get a constant that is not 0, they grow at the same rate. All right, let's look at a couple more problems here. So example 5. Do a cubic, and g of x is going to be a quadratic. So take a second here and think, which one do you think is going to grow faster? Or are they going to grow at the same rate? Do all polynomials grow at the same rate? So we're going to do limit as x goes to infinity of x cubed minus 3x squared plus 1 over x squared plus 2x plus 2. Now, we could do this limit two ways. Number one, we could use rules garnered from earlier in chapter 2, or we could apply L'Hopital's rule. If you remember, back in chapter 2, we learned a rule that allowed you to determine the limit of a rational function based on the degree of the top and the bottom. We'll go over that at the end. So we apply L'Hopital's rule, derivative top, derivative bottom. It would still be infinity over infinity, so we apply L'Hopital's rule a second time. (6x minus 6 over 2). Now if we plugged infinity in, we would just get infinity. Remember, what does that mean? That means the top function won. F of x is faster. Another way we could have done that is, if you look at the degree of the top and the bottom, the degree of the top is bigger, meaning that the limit, as x goes to infinity, is infinity, based on rules we got in chapter 2. So we could have skipped L'Hopital's rule if we remember that trick. All right, let's look at another example. This one we're going to do a general case. We're going to look at not exactly real functions. We're going to look at formulas that kind of represent functions. So let's do two quadratics and talk about how two quadratics will always grow at the same rate. So let's say we had, for the first quadratic, the general form ax squared plus bx plus c. Remember, a, b, and c in this case are constants. And for our g of x, let's make up another quadratic similar fashion, dx squared. I'm not going to use e because that stands for natural log, or Euler's number. So we're going to do f times x plus g. Now, if we apply L'Hopital's rule to that, we will get the limit as x goes to infinity of 2ax plus b over 2dx plus f. And that would require L'Hopital's rule a second time. And we're going to get 2a over 2d. Now 2a over 2d is going to be some constant. Simplifies to a over d. But it's going to be a constant, meaning that those two quadratics, no matter what numbers we put in what places, have to grow at the same rate. All right. Let's look at one more. And this time we're going to deal with one that has that we're going to use the transitive property to get around what would be some horrible work. So let's start with functions. F of x is equal to the square root of x squared plus 5, and g of x is going to equal quantity 2 root x minus 1 quantity squared. So we have to compare this to something that we think is going to be a similar rate. When you square root an x squared, it's kind of like x, which means it's kind of like a linear. So I'm going to compare both of these to the linear functions. What's the simplest linear function to compare to? It'd just be y equals x. So I'm going to compare f of x to y equals x, and then I'm going to compare g of x to y equals x, and then transitivity will let me state the conclusion to this problem. All right. So let's start with the first one here. Limit as x goes to infinity . Oh, 1 second. Got to fix that real quick. Okay. Limit as x goes to infinity of square root of x squared plus 5 over x. And this is a trick you're going to need to know. I am not going to use L'Hopital's rule because doing the derivative at the top is going to get real messy when it starts to involve chain rules. So what we're going to do is we're going to change x into an equivalent form. We're going to make x into the square root of x squared. X can be the equal to the square root of x squared, because if you simplify square root of x squared, it's just x. So I'm going to replace x on the bottom of my limit ratio with that. Now that I have a square root in top and bottom, I can combine them into one square root of x squared plus 5 over x squared. Now I can split, sorry, that should be an x squared. I'll get that in a second. We can split that into two fractions, x squared over x squared, which would be 1. There we go. And then minus 5 over x squared. Now if we plug infinity in, we get the square root of 1 minus 0, which is 1. That means that f of x grows at the same rate as x. So what about the other function? Well, limit as x goes to infinity of, again, we can put these in either order, but if you have a complicated one, it's usually always good to put it on top. Allows more flexibility with the fractions. So on this one, I'm actually going to make it the square root squared, just in the reverse order, because we have a squared on the outside on top. So instead of the square root of a square, I'm going to do a square of a square root, just the reverse. Now I can combine them all into one parenthesis squared. And then I can do simplification like I did in the last one. The 2 root x over root x will cancel to 2. And the 1 over root x. And if we plug in infinity, we'll get 2 minus 0 squared, which is, of course, 4. So those grow at the same rate. Even though the number is different, if it's any constant, we get the same rate. So, because f of x grows at the same rate as x, and g of x grows at the same rate as x, by transitivity, I can say both these functions, f and g, grow at the same rate. So that's the beginning. We'll move on to section 8.2, the second part here pretty soon. Thank you guys for watching. Hope to see you next time.